is you go to 1617 tutorial stress concentrations, and you open up stress concentration models V2. Actually, drop that onto your. I don't know why that didn't work. I've had a bit of a nightmare this morning with ANSYS trying to get the folders working. Right, so we'll have to do this from scratch. Anyway, it doesn't matter. I meant to do it from scratch anyway. So make sure it's on your desktop and call it Tutorial 9. So did you follow that? So on the L drive, mech-eng, EGA324, and go into last year's tutorial assignments, and you'll find the stress concentration models, V2. Okay? You can either open it there directly and save it onto the HUD, or just copy it onto your desktop, and we'll work on the desktop. We'll use this, and I bet none of this is going to work now because I'm doing it all from scratch, but all like all good things. Right. If you've managed to find the right ANSYS file and copied over and opened it up, you'll see a series of analyses like that. They're all transient structural. Now, we had a quick look at on tutorial 5, 6, 7 when we did the bridge at a transient structural analysis. And now we're just going to predominantly use transient structural analysis, but in 2D with a very simple geometry. If you look at your first analysis there, and you open up geometry, you can see what we've done there is we've imported a CAD file directly from SolidWorks. So this is a 2D surface done in SolidWorks, and you'll recognize that shape as that is the actual profile of the tensile test bar, which you'll be using in experiment E3 down the stress concentration probably next week when you do your experiments. So you can export from SolidWorks in formats, different formats, but to be able to create a surface, you've got to do it in a certain way. The import is really simply you just use the import function here, file, import, external geometry file there, and it'll come in. So easy peasy, that's what it looks like. I wish all geometries could come in as easily as that from CAD. But what I'm going to show you is that we can model this, and what we're going to do is we're going to fix it on one side, we're going to pull it on the other. We're going to use a transient structural analysis. Okay, but before we do that, we're just going to check that we've got the geometry in. I'm going to come back to the properties that we allocate to this later on. So we're going to do this in 3 steps. Just for the time being, you're just going to assume that we're going to use a stainless steel NL at the back of it, and that's not my initials, that's nonlinear. So it's got linear properties in there. You can look at check that the geometries come in, it's what you expect. We have allocated a couple of sizing functions here on the mesh, which we've been through these before, they're really easy. What we have set is, so if you right click, insert, put in a sizing there, I'm not saying you do it now, just that's how you would get to this body sizing. And we've overridden the default size to get a 1 millimeter element size on that mesh. We could change that, we could make it smaller, so 0.5, and you can generate a mesh for that. Now, he says confidently, yeah, it does. Okay, so we've refined our mesh from where it was, from a 1 millimeter element size, and we've gone down to a 0.5 millimeter size. Now, what you can see there is that we're putting a lot of effort into meshing up this geometry. And we've got other functions enabled here on sizing such as the proximity to the boundary and the curvature of the boundary, propagates into the mesh. But that's giving us a singularity at this point here, where we've got some pretty ugly looking elements which are distorted as a consequence of having set those sizing functions. So we could probably work quite hard, but I'm feeling a bit lazy at the moment. And on top of that, I'm thinking, well, why do we have to mesh up the tabs? What's the point of meshing up the tabs of the analysis? So if you think about a uniaxial tensile test, you're looking to get a uniform stress distribution through the gauge section of the test piece. Okay, the tabs are there just to focus the stress in the uniaxial stress down through the gauge section. So we don't really need to model what's going on around the fillets here coming down into the gauge section. So we could actually shorten this and literally just focus on a rectangle around the length of the gauge length. And in that case, what we can do is we can have a really good mesh. But what I'm going to do is set that body sizing back to 1 millimeter, just because otherwise it'll take forever to run. And we'll just generate the mesh on a 1 millimeter mesh size. So you get slightly coarser mesh. And let's have a look at the boundary conditions we set. These are very similar to what we're going to do throughout, even when we do a simplified geometry just with the rectangle of the gauge section. We're going to look at having a fixed position on the left-hand side here. So to do that, you click on the analysis, transient, insert, and then you've got all your boundary conditions come up. So you can pick a fixed boundary condition. You can select the line on which it's fixed. So you can fix that one and then apply, and that gives you a fixity. That means, actually, in fact, we've got two here, so we don't need both of them. So that second one I created, we can delete. The other boundary condition, what we're going to do is we're going to allocate, because this is a transient analysis, allows us to put a velocity boundary condition. And the velocity boundary condition we're going to apply on the right-hand side. So basically what we're going to try to match is the strain rate that we apply on the uniaxial tensile test machine to the velocity boundary condition that we're going to apply here. So in the same way, you left-click on transient, insert, and then you pick out velocity boundary condition. So this comes in X, Y, and Z. I should have mentioned, I think that, I'm not quite sure why this is working in giving me 3 components, but anyway. Again, here, we're going to select the edge tool, pick that right edge there, and then we're going to put a velocity in there, which is in the positive X direction. So roughly we're looking between 1 to 3 millimeters per minute. So that's 1 to 3 divided by 60 millimeters per second, which I've been using 0.0167 there. We don't want any movement in the Y or Z directions, so that's how we would put the fixity. So we're going to delete that one, just go with the one that I created earlier. So there. Now, in terms of the analysis, I've tried to make sure that all the simulations that we've done on this, from this point onwards, are as much as possible replicating a uniaxial tensile test, so that we can focus a bit more on the elastoplastic and the elastic models that we're going to use and the material properties, rather than worrying about so when you put a tensile test specimen on the machine, you don't really know. You know you're going to play with the strain rate a bit, but you don't know how long it's going to take to break. So you put it on. And in that same case here, we don't know how long it's going to take it to break, but we're going to put 1200 seconds in there and hope that sometime during that 1200 seconds it's going to break. The other thing as well is that then you have to define a set of time steps because it is transient. So we're using an automatic time stepping, which means that the program ANSYS itself is going and trying to find the best time step for the simulation. and it'll sometimes iterate around. If its time step feels too big, it'll go back and shorten that time step and redo that same time step. So we're using automatic time stepping, but what we do have to tell it is more or less where to start. So we tell it, we'll start at 1 second, and then you'll have a minimum time step of 0.1 and a maximum time step of 10 seconds. Your maximum time step there will make sure that you don't have it running forever. So you have 1200 seconds. Hopefully it won't go below 10 seconds and take forever to run. With that setting on the analysis, there are more things we could go into, but we're not going to right now. We can literally, we're ready to solve it. So if I remember correctly, this didn't take too long to run. So you can hit solve at the top, or you can right click on solution and hit solve. What I've got enabled there is the output called solution output called forced convergence, which gives you an idea then for each of the sub-steps how well ANSYS is dealing with the combination of material properties, model that you've selected, the geometry, the mesh. All of these things are encompassed in the way in which the solution converges. If you start to see a lot of red lines here, you've got a problem, and then you're going to have to delve into where that problem is coming from. Most of these green lines here at each of the substeps, it means that substep is converged. It means that within each substep, all the iterations that you're going through are managing to meet the convergence criteria which is set within the program. So at the moment, we're doing okay. Although we've set 1200 steps to as a maximum time steps, and we're only up to 5, and it's taken 30 seconds, a minute, what we'll find is we're not going to actually need all those 1200 steps. So I can't remember exactly where, but I think around about 120 seconds this thing will finally die, and that's one of the rather unelegant things that happens in ANSYS, is that you can solve a linear elastic problem, and you will rarely get any problem, and it will keep on converging, and you'll keep on getting the most ridiculous answers in the world. You get this massive deformation post where your yield stress would normally be. When you enable some of the nonlinear plasticity-based solutions which are available, which we're going to go through in a bit more detail in the properties in a minute, when you enable those, post the yield point, so post the elastic yield point, it becomes a very complex nonlinear problem. And ANSYS handles it in the best way it can, and it does quite a good job. But there's a point through the plasticity, the hardening rules, and you get the non-returnable deformation post the elastic yield, and it does quite well. But what it can't do is do exactly the same as a tensile test, where it gets up to the upper tensile point strength and then fails, and it doesn't match the failure point. So you've got to watch that and have a look and see how closely it matches. But I'm actually, and that's when it gets a bit messy here, and you'll start to see the convergence starting to get a lot of red lines coming in, and it'll tell you, oh, all sorts of errors are going on and stuff. Anyway, me having waffled on for a while there, and I still haven't managed to get it to converge, so maybe we'll give it a couple of seconds to run through. So one of the things that, well, we'll have a look at the results now, but having used this entire mesh here coming through from the CAD, having meshed up the tabs of the tensile test bar, to a certain extent, although we're replicating the problem much more accurately than we can do later in a submodel, we are wasting a lot of effort trying to solve in these regions. And we're also introducing a level of error because of these poor meshes in that location. Have any of you guys hit the run button? Are you running the problem at the same time? Yeah? Is it running through now? What kind of time steps are you on now at the moment? Well, I set the time step slightly smaller than I intended here. I don't want to stop it now because I want to have some results to show you. So if I stop it now, we're going to have to basically rerun it with a smaller time step, which I don't want to do. So I'm just going to leave it run a bit. And you guys can have a nattle chat, whatever you want to do, and we'll come back to it in a minute. I don't know if we'll have any results to show. I can't remember if... oh, we have. All right, okay. So actually, the results don't look too bad. I mean, that's sort of what you would expect from... you can see, and this is the point that we were making, is that along the gauge section, you've got what you wanted, which was to have a pretty uniform stress distribution, which is the whole point of the uniaxial test in the first place. And all of this extra gubbins and mesh that we had on the tensile, on the tabs of the sample, show that convergence of the stress flow along the tensile test bar. But it might make absolutely no difference to the deformation at any point along here, which is meant to be pretty even. And also, as you can see, it did take quite a long time. So that was just a 2D problem, and we could have been here probably for another 20 minutes waiting for that to get to the point where it actually goes past the yield and breaks. Well, it's gone past yield already, but to the actual point where it actually breaks. Things that we always want to look at in terms of post-processing. The very first thing we always look at in a stress analysis is the von Mises stress. So by left-clicking on solution, insert, you've got stress tools, deformation, strain, stress, and then various forms of strain energies. And the first one that I always go to is the equivalent von Mises, which is what we'd actually plotted there. So we've got a second instance here. When it puts it down there, you have to automatically reevaluate the results. It doesn't mean it's resolving. You don't want to resolve what you've just done there. It's just putting those results for that particular plot, which is the von Mises stress. Just in terms of post-processing, a couple of quick things. You can plot the, on here we've got the undeformed model and we've got the deformed model. So you can see that necking going on, which is exactly what you get with the machine. And then at some point when you're pulling, you'll get, and if you run this for long enough, you would see it on this as well, you'll see a crack suddenly appear halfway down. Well, you won't see a crack appear in the finite element analysis, but you'll see a plasticity start to occur in certain parts, which will join up. Other things we can look at, contours of deformation. Oh, I don't know. Right. Insert, deformation, total. Evaluate all results. So that just shows you the highest stress and the lowest stress. Highest deformation and lowest deformation, and then the total deformation, which is in millimeters. So that's roughly 16 mil. So we stopped that before it finished, and when you get to your tensile test results, when you do that 1 millimeter per minute gauge, deformation rate on the machine, you'll find that you'll roughly get on these samples about 30 millimeters deformation. What else can we look at? Strain. So because this is an elastoplastic problem, we can now have a look at the plastic strain, and you can see the peak plastic strain is happening along the middle of the tensile test bar, which is where you would expect it. So eventually when you get a high enough plastic strain in the middle there, that's where it's going to fracture and break. Okay, so we're going to close that, right? And we're going to go to the adjacent analysis, B, and we'll have a look at the geometry. So this is a really advanced complex geometry of a square rectangle, all right? But what we've done is we've just made that rectangle to be the same width as the test piece, still two-dimensional, and the same length as the gauge length. So we just use a sketch for that. We've dimensioned that, so in the same way as we did that with a lot of the simple geometries that we looked at previously where we just literally have a height to the rectangle and a length. So this has got a 15 millimeter width and a 70 millimeter length. And that's all we need to do. Apart from, well, we create the surface, and we have that geometry. We've done that many times before. And then we'll go into the model. So now we need to have a little think about what we're doing here, because we're actually going to put on some boundary conditions that aren't ideal. And you need to understand that these boundary conditions are not ideal. So this is always the trick when you subdivide a more complex geometry and model, and you take it down to a smaller section. It's always the boundary conditions that are going to give you problems. So basically everything on the analysis is the same, except this time we can have a very nice, even, coarse mesh, which is going to solve really quickly, hopefully. The analysis settings, exactly the same, so up to 1200 seconds. I think I've used a slightly larger time step with this just to get it over and done with quickly, but you could change that back down to 0.1. We've got a fixed support on the left and a fixed velocity on the right. Okay? So which of those is not the ideal boundary condition? There's only two. Take a guess. No. It's the fixed support at the left isn't ideally right, because what we've taken is we've taken the gauge length, but because we are leaving off the tabs on either end to make it mesh easier and have a smaller mesh, and have a better mesh, actually you don't really have a fixed boundary condition on the left-hand side of the gauge length. So you've actually got movement of all the nodes in X and Y, and possibly if you're solving in Z as well. So by fixing that, you're actually kind of changing the problem that you're solving slightly. So that's the first kind of limitation of the model. But we are interested in trying to capture the material, the model, and look at the different types of model. And what we're eventually going to try to do is then introduce stress razors into a very simple geometry like this, just to look at the difference between the stress razors and compare those. So anyway, for the time being, we'll use the same velocity of 0.0167. So you can solve that immediately on that very coarse mesh, and I'm hoping that we should see under solution information that we are running very quickly. So the simulation time there, you can see again to 380, much larger. They are larger time steps, but the mesh is much coarser, so the whole thing is running a lot quicker. Lots of green on our graph, except at these last steps. So you might get that in your simulation from now onwards. And it's not to say that ANSYS has crashed and everything's gone pear-shaped, nothing's worked. All it's saying there is it's reached a certain point of the analysis beyond it which the results are not real. Even ANSYS knows that its results aren't really very credible. So if you click on the equivalent von Mises stress, you can see it's picked up one of the final time steps. At any time you can select that time step and replot. This is a time stress curve on the bottom, and it gives you the minimum and maximum stresses in the sample. You can run the animation there, and you can see very interesting results on your very last step, where the mesh has completely gone through way past its the limits of solvability. But we're only really interested in two things. One is the yield point, capturing the yield point properly. So there we've got somewhere in the region of 150 to 200 MPa. And then we could say that somewhere along this point here, we've still managed to solve. We're getting this nice long deformation that you get in your when you're trying to capture the upper tensile strength. It's capturing that as well. But those boundary conditions on the left that we set it are introducing a bit of a problem in the machine, in the simulation, sorry. That is not particularly applicable. So yes, you do get the necking, but you're probably not going to get the breaking in the same location. What you can do here is insert, first of all, a equivalent plastic strain to have a look at the plastic strains. There. So then you have to evaluate all results. And it's picked the very last one, which is outside that. But you can see that the plastic strains are increasing quite early on. So it goes past the yield quite early on, and then you've got a significant plastic strain until in the end. So if you picked that last time step, you would see that the plastic strain has become big enough that in this red zone here, the plastic strain has gone from one side to the other, and it's high enough that it's going to cause the test bar to break. So that's very equivalent to our upper tensile strength when we actually do it on the physical test. The other thing that we can insert here is a probe point. So here we go. If you go probe and where's the force of reaction there, and that allows you to work out what the reaction forces are at a given boundary condition. So we can pick the fixed end at the end there, and if we look at the one I've already created there for you there, force reaction graph, you'll see that this allows us to get time and the actual force of reaction along that edge on the left. And when you come to do the experiment, you'll see later on this week, these forces, which are in Newton, this is about 4 kilonewtons, is roughly the sort of strength that you get at the peak, the tensile limit, roughly about 4 kilonewtons. All right. So you can see on the right-hand side of that the reaction forces and the time are tabulated. So you can select all of them, just cut and paste, and put them directly into Excel for comparison later on. Okay, so that covers. I mean, we could go back on this. We could play with the mesh. So that mesh is, like we've done before, through using an edge sizing. We could double up the mesh if we wanted to. So we have a much finer mesh, and this would hopefully give us a better solution yet again. So one of the things I would do on this is, because it is, I would keep those as hard so that we have that mesh. Now, I'm not going to run that through now because that's not what I'm too worried about at this moment in time. We've got some results. We've got forces coming out from the reaction side on that fixity, which are roughly in the right order of magnitude as what we see in the experiment. What I want to go back to now is a little bit more detail on the models that we've selected to run this with, to be able to get those large deformations and the forces and stresses which match the experiment. So before I'm just going to so what we can do is, if we take that model B, and this is where now I think it's probably, if you can, work along with this, because we can duplicate that model and it'll stick it below. So basically we're going to do this in 3 stages. First, we're going to look at the engineering data, the database of properties. We're going to have 3 materials defined in there. We're going to do one with just an elastic analysis. Then we're going to do another one with an elastic perfectly plastic analysis. And then we're going to do another one with an elastic multilinear isotropic hardening rule, which is defined upon experimental data. Experimental data from last year, you guys are going to have to get your own data, but it'll do for now. So with this one, let's call it plain sample linear elastic. All right. let's have a look at the engineering data. When that comes up, see that structural steel, the second one down? If you right-click, delete it. Let's get rid of that. We don't need that. That's the default one that always comes through with the ANSYS database. Okay, so this one here that we've just been using was the very last one that we're actually going to analyze. So what we're going to do is duplicate this, copy, and paste. Oops, didn't like that. Duplicate, the other one, and then duplicate it a second time. Everybody still? Okay, all good? Right, let's go to the first one there, and we'll call it, you can double click and rename it, and we'll call this Multilinear Isotropic Hardening. Right, the second one we will rename as linear perfectly plastic, and the third one we will call linear elastic. Oh, Elasticity. Brilliant. Okay, so that's just naming them. What we're going to do is we're going to be a bit brutal here. We're just going to delete on the third one. We'll go down to the outline tree below. We're going to delete multilinear isotropic hardening, and we're going to delete yield strength. In the second one, we're going to do exactly the same, like that. So now you should have three materials of stainless steel. One, linear elastic. In the linear elastic model, in the linear elastic properties, all we've got is density, Young's modulus, and Poisson's ratio. That's all you need for an elastic analysis. Okay? End of story. Removed anything to do with plasticity, tensile strength, anything above the yield limit. Now, for the linear perfectly plastic model, which is the second one up, right, we're actually going to introduce those. We're going to tell it there's something happening here. So let's say you can see on the toolbox on the left, you can see properties that you can drop on that you want to include. If you open plasticity, yeah, we've got bilinear isotropic hardening. So you drag that down and you put it in there, which it should work. Oh, double click, sorry. Okay. So for that, we're going to have a yield strength of 200, for example, and a tangent modulus of 10,000. Now, just to explain a little bit about what that means. Okay. So what you're putting in here is one step above a linear elastic model. We're introducing a very simple hardening rule, a linear hardening rule. Okay, so in essence, the entire stress-strain curve is made up of two parts: your elastic part, and then a plastic part. And what we're saying is that actually we're going to put that modulus as a gradient of the red line that you see on that curve there. So what I like to put in here as well is just also the no, that's all we need, sorry, for now. Okay, and now if we go up to the top material, which is the multilinear isotropic hardening, okay, so all our elasticity properties are the same, our density is the same, bulk modulus, shear modulus, which are derived from the elasticity and Poisson ratio. But now in the hardening rule, well, instead of having a straight line, which is the perfectly plastic, we're actually going to use the stress-strain curve and the true stress-strain curve, not to be confused with the engineering stress-strain curve, which has come out from the experiment. So from here you can see that roughly our yield stress is somewhere between 150 and 200. We'd have to do a proper analysis to be able to get the actual yield stress or the proof yield stress there. And then you can see that you've got the hardening rule is defined by a curve. What we're not going to do, and what I don't suggest you do, is when you do get your experimental results, yeah, you'll have thousands of points along this curve because you'll be saving them every second or something of the test. What we've done is we've fitted a sectioned set of lines to it. You can have up to about 200 points in the database here, and after that it starts to get a bit funny. So it's you know, precision on this does not mean everything. It's better just to capture the overall trend and magnitude. Anyway, so we've now got those three materials defined in the database in our project, which is associated with analysis H. Okay, so we can run that now, but what I'm going to do is, and what if you can do with me, is to duplicate that analysis. This is what I was doing this morning, trying to get it ready. So what happens is that as we actually start running these results, the results files get exponentially bigger, which is part of the reason it took so long to run. So with this one, we're going to call it plane and bilinear or elastoplastic hardening. So what you can do is to make sure that your properties that you've just worked on are exactly the same. You can link like that. And let's do another duplicate of that. So what I'm going to do now is I'm creating three different analyses with three different models. And this last one is the plane, and by plane I mean the plane sample, yeah. And this one is the multi-linear elastoplastic hardening. Okay, and again we can do the same thing. Let's link our properties through like that, which means that we only have one set of properties. So if we change those properties, all those models, we only change it in one place, they will still be the same in the other models we've created. We could do the same with the geometry and the mesh if we wanted to. Okay, but if we go back to the plane to analysis H and open the model, all right. So the geometry's got a question mark on it because we've changed the properties around. It's asking us. So if you click on surface body and the material, you can see it needs to be assigned a material, and you can see the three materials that we've created there. We're going to pick the linear elastic one, so this is going to be our linear elastic model. Once that's done, you see that everything's pretty much the same as it was. We've still got that rather coarse mesh for the rectangle, so everything else will remain the same. We'll solve it with exactly the same time steps, and we'll leave that run for a minute. If you remember correctly, this ran quite quickly. You can see the cumulative time there is already at 235 seconds. What you can see on the convergence graph here is that you've got a lot less variation, because what's happening here is we're solving the linear elastic problem. There is no nonlinearity. That lack of nonlinearity means that we have a lot less convergence problems. So you've got a pretty smooth convergence curve, and as you would expect, there's no problems with convergence. But actually it's that very lack of problems with convergence which tells you we've got no upper limit. There is no upper yield strength. So it's going to run through all the way through to the 1200 seconds and keep on pulling this material. It's elastic. We haven't defined any plasticity limits. It's just going and going and going and going. And as a consequence, the stresses are building because it's still got the same Young's modulus and everything that defines the stresses by Hooke's law is all in them. So we've got really big stresses. So if you look at them, for example, you can see on this that we're actually in MPa, we're actually up in the sort of 62 gigapascals in stresses. So although we get So if we look at the deformation, the forces of reaction are massive compared to what we're getting from the experiment. Basically, and I don't know if you remember when we can open up, but we'll see it in a minute now as well, that it's gone to the yield point, but it doesn't even know there's a yield point, and it just keeps on going. All right, so that it's just deforming like a rubber band. But the stresses are defined, and they go up high because they're all defined by the properties we put in for Young's modulus and Poisson's ratio. So we get these massive stresses, deformation, all of it would be returnable. So if we were to release that, it would and allow a bit of it would just go straight back to its original size. There would be no change in volume, no change in size. It would be exactly the way it was as it started. And that means that we are also that shows you the limitations of using a linear model. So if you were trying to match your experiment with that, you would be nowhere near in terms of the ultimate stresses or the yield forces that you would see. The deformations would probably not match either what you were getting from the experiment. Right. So if we close that one down, go on to our next one. So this is where we're going to try to use a bilinear perfectly plastic hardening rule, which means, and this again is not by any means perfect. So if we look at the geometry, it's giving us a question mark again. It's asking us to confirm what material you want to use for the geometry. So if you open that, click on surface body, go to assignment, and then on this one, we're going to go for the perfectly plastic one. Now, with this simulation, we're going to have to reduce the time step. So we can run it like that, but it'll just run out. Because it's perfectly plastic, and the way that we set that up, when it goes into the transition between the elastic and the plastic hardening rule, there's quite a sharp sort of transition point in this particular model. ANSYS doesn't like that. It reaches the end of the elastic, and then it'll suddenly. So in order to do that, we need to decrease the time step. So to do that, I would suggest for the time being putting 0.1 there and 0.1 there. And then also, because I know that this is going to actually go a lot quicker, I would suggest that you reduce that to about 15 seconds. And then that will ask you to reduce your maximum time step, which you can reduce down to maybe even 5. Okay? So if you've done those 3 changes in the analysis settings, all else being the same, apart from our material properties, we can solve it, look at the solution as it's going along. So it's fine for that first time step. Oh, it's crashed already. Hey, great. Why has it done that? Let's see. Oh dear. So this is the problem that I had this morning. I think that was partly the reason. Where was it? Perfectly plastic. Anybody see the problem there? What units am I working in? What units should I be working in? Megapascal, yeah, exactly. So what I intended to put in there was to say that's why it kind of broke rather early. Both of these should be input in megapascals. So in actual fact, this should be 200 megapascals, and this should be 10,000 megapascals or 10 GPa tangent modulus. Okay. Right. Anyway, good way of learning. Try not to do that. So now we can go. That will have changed it. everywhere. So if you go back to project, open up Model I, I'm glad you guys are all as awake as I am, so I'm not the only one. Okay, so those properties that we just changed there should have come straight back in again. So we can try again, resolve that. Let's have a look at the solution going through, see what else, see what other errors I made on this now. Well, that's looking a bit better. So a few green lines means that we are getting convergence within the substeps. All right, so now you can start to see a lot more oscillation of those. You could probably, by improving the mesh, I mean, we're working with a very coarse mesh here to try to do it in real time. If you were to refine that mesh, we might be able to smooth out some of these oscillations in the convergence. But they tell you that a lot more is going on underneath the hood of ANSYS there while it's trying to solve these non-linearly. But what I'm interested in here now is to see what the difference is between that linear elastic model, the bilinear elastoperfectly plastic model, and then the more complex nonlinear model that we're going to have a look at now. Right. What is the problem here? There occurred. Not sure what that happened there. It could be that the okay. What, now it's working? Right, it is. The data is there. Sometimes for some reason, God knows why, we may have to insert another instance. Oh, okay. So, yeah. Okay, so this is one of a quirk of ANSYS. Sometimes the results are there. It's still trying to plot at the last time step from a previous analysis. So if you update that and change the time at which it's displaying it to the last time, put in 0 and it'll pick out the last time. So yeah, with that, if you click on the graph on evaluate equivalent von Mises stress and you have the graph enabled, what you can see there is a stress time curve. You can see that through the elastic period here, everything's fine. The stress is increasing roughly to the yield point, which we define in our linear elastoplastic. And then after that, it all goes haywire. All right. It doesn't like the time step we've chosen, but we do manage to retain some of the stresses. So, and also what we're getting is we're getting a limit. So that elastoplastically perfect hardening rule that we've used is enabling us to have a yield point beyond which we will have output in the program to be able to plot. For example, if we were to insert strain and equivalent plastic, and we plot that up, we can see that at that point in time where the maximum stresses were reached, so we hit yield at roughly 2.6 seconds there. Then under the plastic strain, at 2.6 seconds, you start to accumulate plastic strains. And And from that point onwards, they just keep on incrementally increasing. So if we pick any other time steps during that plastic hardening, we keep on going, you can see a point up here where they have now joined from one side to the other, which would imply that the test bar is going to break along that line of high plastic strain. Okay, let's see what the forces, the magnitude of the forces. So if you remember correctly, now when we ran the elastic analysis, the forces just kept on going up and up and up and up, yeah, with time, beyond the point which was obviously unrealistic in any in that particular material. In this one, because we've defined ourselves a hardening rule and a yield point, we're getting much closer to what you would expect from the experiment, which is namely to get to yourself somewhere in the order of about 4,000. So it reaches the yield point at about 3,300 Newton, and then what we didn't get very well, and what we don't have data for, was a modulus, our tangent modulus. We just set 10,000 GPa in there for our tangent modulus. You might have been able to get a better tangent modulus which matches the increment, so it was closer to the experiment, so that somewhere at your ultimate tensile strength down here, at 15 seconds where it's going to break, you'd be up at the tensile the 4,000 newtons that you need. But it's not perfect. We know that, so it's an estimation. So we can go back to our original model, which we ran previously, which is the multilinear elastoplastic model, with our data coming from experiment. So in the same way as before, we have to check with the geometry, because it's asking us now, well, which of those three material properties that you've defined do you want to use? So under geometry, pick the surface body, and with this one, we're going to pick the multilinear isotropic hardening, and with that we can solve it. Luckily this one I did run earlier, so I do know it'll run. And with the time steps of this as well, we're using quite those coarse time steps as well. And the time step size that you choose can have an influence on your final solution. So if you're doing a sensitivity analysis on the model, which you're asked to do anyway for the computational modeling part of this at the end of the course for C3, there's two things you need to check here. Time step, mesh size. And you need to do a sensitivity study a little bit on both of them. Okay, let's see how that's going on. All right. Okay. So these particular values of the analysis settings have been craftily picked out for you to run in real time here. They wouldn't necessarily be the best ones for your solution. So if you've got more time to run this, and you haven't got just need to run it in 1 minute flat in front of 50 people, then I would suggest that you decrease your time step, increase your mesh size. Generally a good recipe for getting better solutions. Here now you can see that having that multilinear isotropic hardening rule, flow rule, past the yield, has given us a much more curved maximum and minimum stress within, as a function of time, as a function of the step. At any point we can pick out the point that we want to look at, so retrieve a result at a particular time step. That's something else which I would suggest, that when you're running your own models later on, you decrease the frequency of the output of the results, so you'll end up with massive files. So you could, here at the moment I've got them just outputting it at every single time step, which is creative. That's part of my problem this morning, trying to get everything onto disk to bring down here for you. So that's something I would decrease if I were you. As you see, if you pick a time step within that series, then all your ticks go to green on the solution. So the first one, let's have a look at the animation of So, not particularly exciting, but while it's not particularly exciting, it's actually very close to your experimental results. So that by having, when you do your stress concentration experiment next week and you pull the plane sample, the experimental data get you for that plane sample is the uniaxial data that you need to put into that multilinear isotropic hardening rule. And that's going to get you very close to the experimental results. And that's what this module is all about. So, apologies. Yeah, okay. So let's have a look at the other thing that's on here, which is the plastic strain. So that you can see increasing from the yield point. And you can see the peak will start to happen. You can see the highest plastic strain on these areas here. There is an influence from the corners, which is not realistic. And this is the problem with having simplified the problem so much to run it, is that we do have these unrealistic boundary conditions on the other end of the tensile test specimen. But for the bulk majority of what we're looking for here, we've got a relatively uniform stress field, which allows us to look at the materials. So anyway, in terms of forces, again, we're much closer to the kind of 4,100, 4,200, which you'll see in the experiment. And even the time here at which you're going to find it, the total displacement and time correlation that you get from the machine is also going to match quite closely. So that concludes about 3/4 of the way through this. I'm just going to show you a couple more things that you're going to need for your computational validation, because what we're going to be doing in the let me just here is the same geometry. So we're just taking the rectangle, and we're going to use exactly the same multi-linear isotropic hardening rule, but with the holes introduced in them. We've also introduced a planar symmetry. Okay, so everything that we always try to do is to try to simplify the geometry, but make sure that at least we're getting the boundary conditions as right as possible. So the symmetry location is introduced at the level of the geometry. Okay, and what we've done is we've split the geometry down the middle. So this is actually twice. This hole is a center hole in the geometry. Otherwise, we've kept everything the same, but what we have done is we've used a method like you saw last time with the fluid. We used in the fluid experiments a set of it's trying to improve the mesh in that location while keeping quadrilateral elements. I don't think it's worked particularly successfully, so I think that we've got a better mesh coming up later on. We've still got a fixed end on one end, and we've got a velocity boundary condition on this end. The velocity we've kept at that 0.0167. I understand that this year as well on your experiments you're going to be running at a higher strain rate of 3 millimeters per minute. So what you're going to have to do is when you go to your models, you have to make sure that you're putting in the equivalent velocity boundary condition for your strain rates. So running that through shows that it doesn't take long past the yield point to actually get the failure running through it. And you can see the necking happening just on top of the notch there. And when you look at the forces, you can see the sudden much lower forces. So that's the first thing to note, is what you're interested in is what happens as we progress the different notches as we go through. So if you look at, for example, the 5 millimeter hole there, oops. What would you expect with a 5 millimeter hole? The tensile is are the forces, ultimate forces, going to go up, or are they going to stay the same, or are they going to go down? Down, yeah. So on that same, so this one's already, I don't know if you guys are getting the, with all of these, yeah, it doesn't like the, we probably have to run it anyway, so I'll just resolve that quickly. Oh, didn't like that. Yeah, okay, that was just a glitch. Quite a few of those today. So this should go pretty quickly because it fails pretty quickly. I'm just trying to keep everything constant except the geometry now and the mesh, obviously. And this one we've introduced a 5mm hole. So where before we had a 2mm hole here, now we've got a 5mm hole. Then there was last year anyway, an 8mm hole sample which almost failed almost immediately as soon as you pulled it. So again, the thing that we're going to be looking at here is to try to take out the upper tensile force and see if that's going to match the experiment. So we're really going almost the other way around here. We're modelling it, we're getting the stresses, all the stresses and strains everywhere, and then we're trying to simplify it so we have force displacement. It should fail now.